The ancient Greeks tell us that Icarus flew too close to the sun and tragically fell to the sea and drowned when the heat melted the wax in his wings. For ages innumerable, that story was a determinant for humanity to dare not dream the impossible, for it will only end with us falling greater. But has humanity ever listened to any warnings? Not only did we just fly too close to the sun, we dared to touch it. NASA succeeded where Icarus couldn't when the Parker Solar Probe became the first man-made object to touch the sun. Welcome to Factnominal. And today, let's find out how humanity rewrote history by making contact with a star. On August 12, 2018 at 3:31 a.m., aboard a Delta IV Heavy rocket at Cape Canaveral, humanity launched its first attempt to touch the sun. The Parker Solar Probe marked the culmination of solar exploration concepts that date back to the late 50s, and NASA realized it for an insignificant price of $1.5 billion. Parker took its name from Dr. Eugene Parker. Dr. Parker predicted the existence of the solar wind in 1958 and also coined the phrase. It's been a long time, but fortunately, Dr. Parker is still with us, and that makes it the first time NASA named a spacecraft after a living person. Dr. Parker also attended the 2018 launch, and that too obviously was the first time in history for a person to see a space mission named after him take off. Reaching the sun required an incredible amount of energy. Yan-Ping Guo from the Johns Hopkins Applied Physics Laboratory, who designed the mission trajectory, said in a NASA statement, "The launch energy to reach the sun is 55 times that required to get to Mars, and 2 times that needed to get to Pluto." Guo also went on to say, during summer, Earth and the other planets in our solar system are in the most favorable alignment to allow us to get close to the sun. Of course, the massive amount of gravity wielded by our sun keeps the solar system relatively in place. One might think that getting to the sun is like rolling down a hill. Once you begin, gravity takes over and does the rest. Not exactly. See, our Earth is moving at 67,000 miles per hour in orbit, and any object leaving the planet begins at that speed, almost entirely sideways. Parker had to decelerate 53,000 miles per hour to move to the center of our solar system. Sounds crazy? It gets even wilder. As the Parker Solar Probe shed almost 80% of its velocity from the sideways trajectory at launch, it was captured by the incredible gravity of the sun. This made the probe the all-time fastest human-made object. How fast? 364,621 miles per hour at last report, to be exact. And when Parker's closest approach is made in 2024, its speed will reach 430,000 miles per hour. That's getting from Philadelphia to Washington, D.C. in 1 second, or New York City to Tokyo in less than a minute. Before we get too carried away with this velocity and its possibilities, it amounts to about 0.05% of the speed of light. And reaching our nearest cosmic neighbor once we leave the solar system, Proxima Centauri, with Parker going full throttle, we need to pack enough sandwiches for a minimum of several thousand years. But we digress. Before reaching our sun, the Parker Solar Probe completed the first of 7 scheduled flybys of Venus, passing through the planet's upper atmosphere and using its gravity to maneuver the probe's orbit to make even closer ventures to the sun. Alright, not exactly the heart of the sun, but picture this. If the sun and Earth are at opposite ends of a football field, the Parker Space Probe will reach the 4-yard line, just outside the sun's end zone at a breathtakingly close 3.83 million miles. This is coming in its closest orbit in 2024. And for further perspective, humanity's closest trip to our solar neighbor was with Helios 2 in 1976, which crossed the orbit of Mercury to only 26.987 million miles from the sun, or about the 30-yard line. What does NASA hope to accomplish by getting the Parker Solar Probe so close to the sun? Quite a lot. The spacecraft features 4 instrument suites to explore our sun for its 7-year mission. Specifically, they will study magnetic fields, plasma, and energy particles and produce images of the solar wind. Solar wind was identified decades ago, but there's much we do not understand about it. Our measurements of solar wind have come near our planet, tens of millions of miles away from its origin and after it's cooled and intermixed. With its amazingly close passes, Parker will trace how energy and heat move through the solar corona and what propels them to reach their speeds. Plus, NASA has a great interest in Parker learning more about solar energetic particles, or SEPs. These are tiny solar projectiles that make the 93 million trek to Earth in under an hour. They can torch sensitive electronics on spacecraft and even pose serious risks to astronauts. And Parker may answer where they come from. SEPs contain a different mix of particles, more of some and fewer of others such as sulfur, than other solar expulsions. Another large looming question for the Parker Solar Probe is what astronomers call the coronal heating problem. The sun's surface reaches 10,000 degrees Fahrenheit. But out in the corona, the thermometer spikes past 2 million Fahrenheit in one of the greatest cosmic riddles. For the first time, astrophysicists will take measurements inside the corona itself and look to solve the riddle. The sun lacks a solid surface, but does have its own version of one with its photosphere. This is the visible surface of the sun from which comes most of the sunlight that reaches Earth directly. There's also the Alphen critical surface. This marks the end of the solar atmosphere and the beginning of the solar wind. Essentially, the sun's gravity and magnetic fields can no longer keep solar material close, and that material leaves the sun never to return. That point is Alphen. Being able to determine exactly where the Alphen critical surface is would clear up estimates ranging from 4.3 to 8.6 million miles from the sun's so-called surface. Even before reaching the sun, Parker served up a surprise. Back in 2019, the probe discovered magnetic zigzag structures in the solar wind dubbed switchbacks, which are sudden reverses in the sun's magnetic field. During its recent approach, astronomers determined that these originate from the solar surface. Astronomers hope to use data from Parker to learn how switchbacks are formed and even why the corona is so much hotter than the solar surface. And now that we are there, the answers are just around the corner. This announcement by Nicola Fox, Heliophysics Division Director of the Science Mission Directorate at NASA, confirmed to the world that Parker had indeed dipped into the sun's corona on April 28, 2021, during the spacecraft's 8th close approach to the sun. Why almost 8 months later? The months in between were needed for NASA to get the data back and analyze energy reactions recorded by Parker to be certain it had actually been accomplished. Now we know that the first touch came in April, with 2 more in August and November. So what exactly happened on April 28th? Remember the Alphen critical surface and the varying estimates on its distance from the photosphere? We now know that, according to early data, Parker crossed the critical surface at 8.1 million miles above the sun's surface. Parker Solar Probe crossed the Alphen critical surface at 933 UT and spent 5 hours below in direct contact with the sun's plasma. The spacecraft dipped below and rose back above the surface 3 separate times, and in the process discovered the Alphen critical surface was wrinkled. Spikes and valleys wrinkle the critical surface, and scientists want to discover how these line up with solar activity, to determine how this activity affects the atmosphere and, more importantly, solar wind. Parker went even deeper and found a pseudo-streamer, these bright loop-like structures that develop over active regions on the sun. NASA describes the feat as flying into the eye of a storm. This eerily vivid description matches perfectly with what Parker encountered. The solar conditions quieted, particles slowed, and the number of switchbacks fell as in the eye of a cosmic hurricane. Fast forward to August 2021. The most amazing aspect of this historic feat thus far may be taking the first photos ever from within the sun's corona, and then making a spectacular 13-second time-lapse video. The Parker Solar Probe flew through structures known as coronal streamers, the stunning streaks of light captured from Earth in photos of total solar eclipses. Even more incredible are the images of our solar system from within the sun's corona captured by Parker's wide-field imager of the Milky Way and multiple planets, including our Earth, from the sun. A mind-blowing feat for humanity, which begs the question: it's easy to imagine middle school students all over the planet raising their hands to ask this most obvious question to their teacher. How does it not melt? Did you say the corona reaches millions of degrees Fahrenheit? Their teacher and NASA will explain it like this: there's a vast difference between heat and temperature. Temperature is the measure of how fast particles are moving, while heat is the total amount of energy they transfer. As for the corona, it is very thin and has few particles to transfer energy. So yes, the particles are fast and the temperature is high, but very little energy or heat is actually transferred to the spacecraft. NASA describes it as the difference between putting your hand in a hot oven and putting it in a pot of boiling water. Neither are advisable, but the comparison works. In fact, Parker's surface is only supposed to reach around 2,500 degrees Fahrenheit. That's all? It's plenty, and that's why the spacecraft has a heat shield called the Thermal Protection System. This is a layer of carbon composite foam sandwiched between two carbon plates. The side facing the sun features a white ceramic coating applied as a plasma spray to deflect heat. What does this mean for the delicate scientific instruments aboard Parker? The sun side reaches 2,500 degrees Fahrenheit, but the protected instruments maintain a temperature of 85 degrees Fahrenheit. And there's also a single gallon, 1 gallon, of deionized water to absorb heat as it passes through the solar arrays and send it back into space from the vehicle's radiator. The next solo flyby for the Parker Solar Probe is in January 2022 and will likely see the spacecraft enter the corona again. And with the Sun's regular 11-year cycle of changes in its magnetic field increasing activity through 2025, the outer edge of the corona will expand, and Parker will have greater chances of being inside for longer periods of time. So what do you hope that humanity learns from our first trip to a star? Tell us in the comments. And as always, thank you for watching Factnominal.